Okay, the third question, right. Photons are emitted by stimulated emission. Calculate the fraction. Photon energy. So we are referring to the photons emitted by stimulated emission. These ones here. We need to think about this transition. So the energy of those photons is 3.14 times 10 to the minus 19 joules. The difference between those energy levels. And the energy used to excite the atom to level U, we need to send the electron from the ground state to level U. So we need that energy. That's what's going in there. Plug that lot into your calculator. Your fraction is 0.095. You may be thinking, well, that's not a fraction, it's a decimal. Yes, we want to calculate the fraction. 2 over 3 calculated is 0.67, for example. Right, we don't like fractions in physics. Right, calculate the wavelength of the light emitted. Well, that would be these photons emitted by stimulated emission. So we need to deal with this energy here. Equals hc over lambda, lambda equals hc over e, 633 nanometers. What causes a stimulated emission event to occur? A photon of energy 3.14 times 10 to the minus 19 joules. Well, it's 2 marks. A photon causes stimulated emission, but we need a bit more detail. I've given my answer specifically for this here. You could talk a bit more generically, the idea that the photon needs an energy equal to the difference between the energy levels. In this case, it's that. It's the quickest and easiest way of writing down an answer that makes sense. Describe carefully in terms of photons the outcome of such an event. There will now be 2 identical photons. It doesn't seem like I've got enough for 2 marks there, but the key bits we want is there's another photon given out, and that it is indeed the same as the one that caused the event. So there are 2 marks worth of comments there. An electron stays in level L for only a very short time, spontaneously dropping to the ground state. Why is that important? The operation of the laser. L remains unpopulated. So there's going to be very, very few electrons there. So there's less pumping required. Much like the previous question, where we had a similar question actually. Why was it important for the, I think, level L to be above the ground state? Less pumping is required actually to get the population inversion, so that's important. We're pumping to get this population inversion. So we've got a diagram of the construction of a laser. How does the cavity design promote laser operation? So this is the cavity here. We want the idea that the mirrors cause the light to traverse the cavity. It's okay, just say the light bounces backwards and forwards between the mirrors. By keeping your laser light in the laser, you are increasing the chances of more stimulated emission occurring. You need the laser photons to cause more laser photons through stimulated emission. Let's have a look at the last question then. Right. So you've got these diagrams here. Calculate the wavelength of the instant photon. That's here. It's got that energy difference. Plonk it into hc over lambda equals the energy of the photon, 695 nanometers. What's the name given to process A? Where's that? Absorption. Absorption. The photon's being absorbed, the electron goes up in energy level. That's not pumping. Pumping is a very specific type of absorption when we send electrons from the ground state to the highest energy level. What happens to the energy of the instant photon in process A? It's used to increase the electron's energy. That photon disappears, the electron just gains the energy equal to the energy of the photon. Name of process B, that's a stimulated emission. We've got an instant photon, it knocks an electron down, I get another photon that's identical out. I've amplified my light. State two things which the emerging photons in process B have in common. They have the same frequency, wavelength or energy. You can only say one of those, because if it does have the same frequency, it will have the same wavelength and it will have the same energy. So 1 mark for any of those. They also have the same phase, they've got the same direction, and they'll have the same polarization, which I haven't talked to you about yet. For the laser to work, process B must happen more often than process A. This requires a population inversion. What is meant by a population inversion? More electrons in the middle level than the ground state. I've just got more electrons here than here. And I think there's more on the other side. Hang on a wee minute. There is indeed more on the other side. Excellent. Oh, great. I need to turn the page back. Draw an arrow to show the transition associated with pumping. Right. Crying out loud. Got the damn pad. There, from the ground state to the highest energy level. Pumping. How much the typical time an electron spends at the top level compare with the typical time it spends in the middle level? Give a reason for your answer. It must spend a shorter time to maintain the population of the middle level. Right. So it's important the electrons don't spend very long in the highest energy level. The reason for that is, I'll turn the page over and I'll show you the diagram. If we pump electrons up here and they stay there, these same photons used to do the pumping could knock them straight back down to the bottom level before they've had chance to end up in this level, and we need them to be in this level to have the population inversion. So remember, this is why we don't pump directly into the energy level we want the electrons to be in, because the pumping mechanism can knock the electrons straight back down. So we need the electrons to stay there for a very short time so that they drop straight into the level we want them to be in. If there's any questions on those, please do ask me. I think working on these lasers should be enough work for the first week. We'll worry about wave particle duality next week. Doug Green, signing out.